Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's check if this differential equation is exact. And if it is, let's solve it using the techniques we learnt in the first two videos of this series. If you haven't yet watched these, then I urge you to do so, as I'll be drawing on the knowledge gained from these in order to solve this equation. I'll drop a link to both in the description of this video. So we're going to solve differential equation 2x plus x squared y cubed dx plus x cubed y squared plus 4y cubed dy is equal to 0. Now we know that for a differential equation to be exact, it must be of the form some function of m multiplied by dx plus some function of n multiplied by dy is equal to 0. And at first glance, it looks as if this equation falls into that category. So let's identify functions m and n. So in this equation, function m is this part here. So m is equal to 2x plus x squared y cubed. And function n is this part here. So n is equal to x cubed y squared plus 4y cubed. And to determine whether this equation is an exact differential equation, we need to look at the partial derivatives of m with respect to y and n with respect to x. And if these partial derivatives are equal, then the equation is exact. If we take the partial derivative of m with respect to y, we see it's 3y squared x squared. And the partial derivative of n with respect to x is equal to 3y squared x squared. And so from this, we can see that the differential equation is exact. We saw that we could find the potential function f, which would be the solution to our differential equation, by solving equation 1 or equation 2 shown here. And for this example, I'm going to be using equation 1. So in this case, our potential function f can be found by solving the integral of 2x plus x squared y cubed dx plus g, which is a function of y. And evaluating this integral with respect to x, we find that the potential function f is equal to x squared plus x cubed y cubed divided by 3 plus g, which is a function of y. Now, to find the function g, we can equate the function n to the partial derivative of f with respect to y. And we now know that, having evaluated the integral, f is equal to x squared plus x cubed y cubed divided by 3 plus function g. And so n is equal to the partial derivative with respect to y of x squared plus x cubed y cubed divided by 3 plus function g. If we now substitute for n, which is this expression here, and take the partial derivative, we get x cubed y squared plus 4y cubed is equal to 3y squared x cubed divided by 3 plus g prime. And we see the 3's cancel, and the y squared x cubed cancels with the y squared x cubed, and this leaves g prime is equal to 4y cubed. And so g is equal to the integral of 4y cubed dy. And evaluating the integral, we see that g is equal to y to the power of 4 plus a constant c. And now if we plug function g in here, we find that our potential function f is equal to x squared plus x cubed y cubed divided by 3 plus y to the power of 4 plus a constant c. And setting our potential function equal to a constant, we have x squared plus x cubed y cubed divided by 3 plus y to the power of 4 plus c is equal to constant k. Combining constants c and k into new constant c1, we find that the general solution of our differential equation is x squared plus x cubed y cubed divided by 3 plus y to the power of 4 is equal to constant C1.